So again, as a way of introduction, my name is Jignesh Bhadaliya. I go by Jig. And the topic of interest today is storage-aware job scheduling. So I noticed storage being brought up a little bit in one of the earlier presentations. So want to talk through that in a little more detail. I work at Dell EMC as the CTO for EDA specifically. For those of you that don't know EDA, think of EDA as the subset of HPC, your embarrassingly parallel distributed computing type jobs. And so with that in mind, let's kick it off and say, why am I here? Right? And so in the bigger scheme of things, I'm here to achieve nirvana, right? So no, you're not in the wrong room. If I wanted to, go through the spiritual journey, that would be a different talk track. But with respect to HPC, I'm looking for a nirvana of a different kind. I'm looking for a nirvana of all components within the HPC compute grid to work seamlessly, right? Compute, storage, networking, applications, all of it working seamlessly, right? So, I wasn't really a good student when I was in college, but I do at least remember the title of my courses. So this is a topic that's well covered in ECE Control Systems undergrad course, right? You may recall open loop and closed loop systems, right? So any high performance compute infrastructure today, storage is an integral part of that infrastructure, that environment. However, there is no standard mechanism today that ties compute and storage together. I heard hooks, I heard a lot of cloud-related talks, and perhaps hooks is the answer, and we'll end with that. We'll start with that, and we'll end with that. But the problem that a lot of the EDA customers face, and maybe some of you face as well, especially if you're having an embarrassingly parallel, loosely coupled type workload where jobs run independently but in large numbers. There's a high degree of unpredictability and a large number of workloads that run in the EDA compute grid. Do you guys in the greater HPC have a similar problem where there is unpredictability of workload, or are the workloads fairly predictable in their I/O characteristics? Unpredictable, raise your hands. Okay, so that's good. That's good to hear, right? So if you take a time scale and if you look at the set of workloads that come and go, there's a high degree of unpredictability, and there is a lot of contingency on other components besides just storage. So I'm going to back up a little bit and go through some reference architectures and then talk explicitly on the EDA reference architecture, which is near and dear to my heart and I know well. But you take your typical HPC compute and storage infrastructure 20, 30 years ago, this is what it looks like. Maybe it still looks like this today for some of you. Essentially a way to log in, a large compute grid and storage associated with it with some kind of networking, right? Then the evolution of that is that, okay, let's separate the storage from compute, right? So you have a set of processing horsepower through a set of servers that serve your compute. So you go from a distributed file system to a parallel file system. And then, perhaps with the evolution of Ethernet with 40 gig and 100 gig, some type of a centralized storage solution. Of course, I have my shameless plug there for EMC Isilon. But the talk here won't necessarily focus on any specific type of technology. I'll switch gears here to a more complete diagram of the EDA engineering infrastructure. I heard Intel's in the room, right? So at least there is someone else besides myself that knows EDA. If you look through this diagram, this may be similar for any other HPC infrastructure, right? 20 years ago, maybe more, you would have had Unix workstations, but today everyone has a Windows laptop or a Mac laptop. And then you log into some way, through some type of a thin client topology into a login farm for whatever you may be doing interactively. And then you submit your jobs to a large compute grid, right? In EDA, it's not uncommon for that compute grid to scale into hundreds of thousands of cores, right? I'm easily hearing over 100,000 cores in a compute grid at tier 1 semiconductor shops. Then you have tens of petabytes of storage. Central storage. EDA is one of those few shops, few workloads that still have all the data centralized, right? There is no concept of a distributed file system. Everything is on shared NAS storage using AutoMounter and good old NIS. That's the topology, the workflow. Is highly unpredictable because a given user can launch thousands of jobs, sometimes tens of thousands of jobs. Jobs are tied to a compute core, right? So a core is a job slot, and that's how the workload is carried out, right? So as you think about that. And kicking off with the spiritual talk track there, who is God? Who plays the role of God in this architectural diagram? Who's the controller? Who controls access to how all the components are utilized? And the answer is simple, right? It's the job scheduler. It's grid computing, in distributed computing. It's the job scheduler, and then I was told that I'll get bonus points for plugging in PBS Pro. So lifted directly off of the website, a PBS Pro, Altair's industry-leading workload manager and job scheduler for high-performance computing HPC environments. So joking aside, let's shift from the scheduler to educating a little bit on the storage there. And every storage system, doesn't matter the storage system that I'm responsible for or any other storage systems out there in the world, has a performance capacity, right? Performance upper limit. Think of it as a freeway system, right? At rush hour, so I'm based out of Southern California, so this analogy works really well for me, right? So, it's at rush hour, the freeways are oversubscribed, and similarly, when you get a burst of your jobs on your compute grid, sudden burst, your storage is oversubscribed, right? So, you can certainly scale wider, right? Whether it be through the distributed storage solution you have, through the parallel file system you may have, or through a scale-out NAS. It doesn't matter. You can scale, but nevertheless, there are still practical and economical limitations, right? You don't just scale performance simply because you can scale it from a technical perspective. There's an economic and cost associated with how wide you can go. There are a number of reasons why you may saturate your storage. Undersized storage solution for peak demand is one. This is not a common one, right? If you're working if you're working diligently, if you have a good storage team, then you've sized appropriately for your throughput and your IOPS demand. The most common ones are the unanticipated and abrupt and sudden demand to a large number of jobs, right? So that's what I equate to rush hour. Then there is the other one where maybe some intern started and doesn't know the workflow and the methodologies, and there is some accidental ramp up of certain type of jobs. And that could also bring the entire infrastructure to a halt or a slowdown at least within that reference architecture as you refer back to that. And there could be some runaway jobs that the users may not even know about, right? So does all of this sound familiar? Am I off the track? Or, okay, I see some nods. So that's, long story short, storage systems do have its limitations. This is a good way of understanding what the limitations are. The numbers aren't relevant. The shape of the curve is what's relevant. On the vertical axis there is where you have the response time in latency, right? Or latency representing response time. And then this is an industry standard benchmark of Spec SFS 2014 software build workload, comparing Isilon, various models of Isilon between generations. But what I want you to focus in on is kind of that, skyrocketing upwards trajectory after a certain point, right? After a certain point, you essentially saturate the storage. Can you get more than one F800 and scale that twice? Yes. Can you get 3? Yes. Can you get 4? Yes. But at 4, the numbers will be 4 times, and I'm sure your users can still saturate those numbers, right? So there's a sweet spot to be in for this curve, right? So that sweet spot is your cutoff threshold for the latency. So let's call that 2 milliseconds. So if you draw a line through the 2 milliseconds there, and you try to cut that off there, essentially what you're saying is you want to stay. I'm sorry. You want to. You want to stay here. You want to stay underneath here. Maybe this works better. You want to stay under the 2 milliseconds mark. Otherwise, what's going to happen is the jobs that your engineers, your users are running are actually going to start taking longer. To give you an example, for example, if you're driving the storage at 4 milliseconds, your jobs will take twice as long to complete, given it's 100% IO bound job. So maybe it will really take more like 1.5x or something, right? But you get the point, right? So you want to stay within the boundaries, right? That's kind of the idea here. So today what happens is, more often than not, storage systems are saturated, and there is a reactive approach to addressing this issue. That reactive approach is somebody says the internet's broken, or my jobs are running slow, right? So, I used to work, many years ago, I used to work help desk at my college, and I used to have students come up to me and say, my internet's broken. So that stuck with me. But today in the HPC world, people will say things are slow, right? And then you kind of try to drill further, and you say, okay, all right, let's see what's going on. When the problem comes to storage, the first thing you do is you look at the directory path within the POSIX nomenclature to say, hey, okay, this is where you're driving a lot of the IOPS. And then you try to translate those paths or that path into the number of clients or a client, usually a set of clients in distributed computing that may be hammering against that given path, right? And then you log into those clients, you identify who's running what. and you call up that user, and then you throttle your jobs back. Guess where? From the job scheduler, right? So it's, this is fine. This is a manual reactive approach. This is what most people may be doing today in the room. Some people may have some custom scripts. Here's an illustration by example, right? A real customer, real life scenario. You look at the file system, directory IFS-SG is driving bulk of the operations, bulk of the IOPS on the storage backend. And you drill down further, and it just happens to be that this customer has the directory system laid out such that it's, the directory name actually refers to end user. So you call up Mr. Ankur S and say, hey, Mr. Ankur, you're kind of taking everybody down, So that's one way to approach it, right? Of course, as you look at this, you go, well, you're a storage guy. Why don't you address it from the storage end? Sure, we can do that. So one way to do it is to do it, independently of all the other components within the reference architecture and play defense, right? And that's perhaps QoS at storage level by path, by client, by a set of users, by a set of clients. And then, you tweak knobs on the storage sides to make sure you get, the IOPS and the throughput to a given set of consumer, right? The other way to do it, which is probably the more elegant way to do it, is to control the offense through the job scheduler, right? So throttle the consumer through the job scheduler, limit the number of running jobs, right? By, either by user, by path, by queue, whatever have you. And some of the corrective actions that you may take may be, you pend some heavy IO jobs, you stagger jobs, perhaps you restrict additional jobs from entering. So if you look at this, what we're trying to accomplish, again, so it looks like I am a little ahead of the slides here. What we're trying to accomplish is more of a sophisticated policy-based self-learning engine, right? With artificial intelligence and autocorrection, right? That's essentially what we're looking at. If we can have a self-driving car, I'm sure we can close that feedback loop in the HPC diagram, right? So that's this slide here, right? And perhaps some things to consider as you look at the implementation. So what's really demanded here is automated decision making, which is more proactive. And that can be divided up into two different categories, two different buckets. One is decision making at dispatch time, and then the other is post-dispatch, right? So at dispatch time, think of it, in the freeway analogy as that on-ramp light that you have, right? That may not be good enough unless there's a feedback loop, right? Because those lights are just timed. So essentially what you need is sensors, right? And that sensor in form of storage, for example, may just be storage latencies. And we'll talk a little bit more about additional sensors here as I close my thoughts. So at dispatch time, you're controlling the flow. That's one thing that needs to be addressed. The second thing is, if you think about embarrassingly parallel workloads, you could have scenarios where within a split second, end user can launch 5,000 jobs, 10,000 jobs, take your pick, right? And take your number, depending on how large of a shop you are. Maybe the gate lets those jobs through at that split second because the latencies are healthy. But when the jobs start running, And then post-submission in execution time, you also may run into some type of a saturation scenario. And at that point, again, if there was a feedback loop, then you can feed that information back and say, hey, look, pen some of the jobs. We need to stagger these jobs, right? And let traffic through in a more appropriate manner. Again, to stretch the analogy of the freeway, I don't know if you've ever seen this or not. You every now and then you see a highway patrol cop coming into the middle and kind of doing like this zigzag thing to halt the traffic for a while and let the contention clear, right? So think of it that way, right? And a couple more slides and then I'll take questions. But again, real life scenario of a customer that's doing really well in terms of correlating the number of jobs with the storage latencies there. So the green line that you see there is the number of jobs. The vertical axis on the left there represents the scale for the number of jobs. The vertical axis on the right there represents the latencies for the storage. And the horizontal axis just represents time scale. So as you look at this, essentially, you can see there's a direct one-to-one correlation of as the jobs come in, and in this case, 2,500 jobs, your latencies are well above acceptable threshold levels, right? 40 milliseconds. So essentially, you can let this continue. That's fine, and it looks like it did continue in that manner without any action, right? But the net result here is that all 2,500 of those jobs experienced 40 milliseconds, 20 to 40 millisecond latencies. Whereas what you could have done, if you had a feedback loop, is you could have said, look, you know what? I want to be in the 10 milliseconds range. Therefore, I'm going to throttle this back to more like, 250 jobs or something like that, and I'm going to let them through. And if you look at 10 milliseconds, at 2,500 jobs, the latencies are 120 milliseconds. So if we're saying, hey, we're going to do like, maybe 500 jobs or something, then you're cutting the latencies down by 1/6, right? So, you have to work out that math to say, do I want to be the traffic cop or not? And does it benefit me or not? But the idea here is perhaps throttling the number of jobs and staggering them gets everybody home on time, right? That's kind of the idea. So last slide, smart this and smart that, smartphones, smart things, right? So smart plugins. I hadn't heard of the term hooks yet for PBS Pro, but I think this hooks right into smart plugins, right? And the conceptual thought I have in terms of plugging into the job scheduler, right? So what I foresee here is a set of plugins, right? Not just storage. Maybe there's a storage plugin. Maybe there's a network plugin. There's maybe application-specific plugin. Maybe there's workload-specific plugins. So that you model this type of jobs that are short-running jobs or something, and maybe you want to take certain action through that feedback loop, right? So again, today, the HPC diagram is an open loop system. There really needs to be a closed loop system, and the control decision needs to come proactively through the job scheduler. Furthermore, in terms of call to action, perhaps some sort of standards. If you look at that high-level diagram that I stole from Wikipedia in terms of kind of that feedback loop and sensors, what we're really talking about here is sensors, right? And a standard of those sensors in terms of what those sensors report. So if you think about the storage sensor, maybe the storage sensor is going to report you the average latencies, the peak latencies, the standard deviation, the throughput in use, etc. Right? So on and so forth, right? And I was actually talking to, I'm sorry, I didn't catch your name. Bill. I was talking to Bill at break time, and I think the idea of hooks it's spot on in a sense that perhaps if some of you have already done something like this and is available for the community, make it open source, extensible, right? With that, I will open it up for questions.
Cool. Gabe, sorry, questions?
Gabe's neighbor, I'll take over for Gabe. So we've put a lot of thought into this, looking at mostly the case of the user who doesn't know what they're doing, hammering a parallel file system, right? So that tends to be the way that we fall apart at a cluster level. And it seems to me that's going to be one of the probably last cases you can catch, because you have to almost look at the script they're submitting, right? Look at the job they're submitting. In our case, it's a Wild West. The user can put whatever they want in there. There's no abacus and nice list of applications. So whatever we can get to catch that case on the storage side actually ends up being the solution for a site like ours, right? So we're looking more into that, the QoS pieces and how do you schedule the storage workload. But from the job scheduler standpoint, we are thinking about that. How do we incentivize users to tell us more about their job, right? Give us more meta information to understand, which file systems do you intend to use with your job? What are you going to target with that? And so there's no standard for that. It's just going to be how we phrase it to the users, how we ask them. But any direction, any improvement in any of those things will greatly help a cluster at scale, particularly, but even just under a load-driven file system scenario.
Yeah, so there's a couple of ways to address this, right? So one of the things that you touched on in your set of comments, I didn't catch the question, but in your set of comments was input from the user at job submission time. That's definitely one way to catch information, but that may not be sufficient. Because the information should be really collected real time and proactively from all the components. And let me explain what I mean by this. One of the things that is available in a lot of the job schedulers is the concept of resources. And having reliance or putting the onus of specifying the set of resources required on the end user will always almost definitely result in users saying, I need the maximum set of resources, right? Give me the fastest server and the fastest number of IOPS, et cetera, right? So you're not gonna get, you may or may not get useful information. So the idea here is to actually query all the other components in real time, in action. So when in your earlier portion of the comment in terms of kind of, hey, a user hammering away at the file system, taking the whole reference architecture down, really the answer there is to be able to get that information from the file system to say which user is actually inflicting this injury on this file system, right? And so any given storage solution has a set of commands that give you statistics, right? That may give you statistics through path, that may give you statistics through client, and that may also give you statistics through which users are doing what. Because the storage system in the end will actually be tied into your auth provider, meaning to say NIS or LDAP or whatever, AD, whatever you have, right? And because it's tied into that, it knows which user is actually driving the load. So you want to query that storage system or any other component in real time to say who's inflicting the injury, rather than having reliance on input from the user community.
Others? Questions? seeing any questions. Okay, thank you very much.
Thank you.